Hello everyone. This is the tutorial for lab number 3, projectile motion. The lab that you can find here in Bright Spaces. You can download it like the previous labs. If you use Word, you will have a file like this. And just like the previous two labs, you will have a website that you can access for the simulation of projectile motion. You have part A and part B for this lab, calculations and questions, so similar to the first two labs. In this lab, you're going to be exploring the lab of projectile motion from the Colorado applet. So you can just copy paste this link. And make sure you click on lab. So the idea is to explore what happens in projectile motion that we have been studying in the lecture. Now, let's adjust the parameters so you can actually do some proper exploration of free fall projectile motion and then projectile motion at a given angle. For part A, you are going to be using 0 degrees. You want to have a type of motion like this. That's a free fall projectile motion, no angle, just horizontal velocity, which makes the mass move on this direction, in this trajectory. The height is important. Make sure it's at least, well, it can be a bit more, it can be a bit less. You cannot go more than 15, so 10 is fine to begin with. And then you can do a couple more trials with different heights. Make sure the speed is not too high, so you can actually observe the horizontal range, right? You can use this for that. For part A, you are going to have to do some calculations. So for part A, you are going to calculate the time it takes for the projectile to fly in the air. So if you have this setup, then 10 meters equals to 1/2 gravity times time squared. So time is 20 divided by gravity square root, right? Now gravity is 9.81. Is the software, so you can just use a calculator and we can calculate the time. So 20 divided by 9.81, and then we take the square root. That's 1.42. So if we use freezing fix, 1.43 seconds. So why do we need this? Because then you're going to use that time to calculate the horizontal distance, or to calculate the horizontal velocity, sorry. The horizontal distance is given in the software, there. So the range is 22.8 meters, right? That's what we have here. And we know that range is the x value, the horizontal distance, that's equal to v times time, where v is the horizontal velocity of the projectile. And there's not really a vertical because there's no angle, it's 0 degrees. So v is basically the initial speed, right? The magnitude of the velocity is speed, and because there is just one component, they both are the same. So 22.8 equals to v times time, which is 1.43. So v is just 22.8 divided by 1.43, 15.94, so 15.9 meters per second. And guess what? That matches almost the one in the software, right? So you're gonna do, you have to perform an error percentage, which you know is just the absolute value of the theoretical minus experiment. Yeah, can just use that. Theoretical minus experimental divided by theoretical times 100%. So 0.62. So yeah, it's a simulation. So you're gonna get really good values of percentage difference or percentage error in this case. So that's part A. Don't forget to submit these calculations in the file. So the way I will suggest is like you want to do some space here, and then you can do first trial, and then you can just copy this. Just be careful with the units, right? So I'll put there initial height in meters, and then there you are. Make sure it's good, that I can actually see it. And then you may want to have like a snapshot of this. You can use a sniping tool. Just one, by the way. You don't have to do all of them because you're supposed to do free trials. Yeah, for free different values of height. So you can just put that in there. There, right? Yeah. Or even like smaller than that there. There you are. So for the second and third trial, you can reset this and then you can change the height. You can do 8 meters and then the same, or maybe just add more speed, maybe 20. And then there you are. And you do the same. So here the range is 25.6. And use the same procedure. This will be 8 now. You will find a different time. The range will be 25.6. The same equation. You find your theoretical speed or velocity, horizontal velocity, and then you do a percentage error based on this value here. So the first part is very easy. All right. The second part. Now you're going to do an angle. And it says in the instructions that the angle has to be between 30 and 60 degrees, and the velocity should not be less than 10 meters per second. So that's so you can do this. There. 10 meters the same. 15. That's so you can do that. See that? Oh, great. If that happens, you see it doesn't, I don't know why it doesn't go beyond. It's weird. Okay, that's better. A lot more, maybe. Let's do 14. Yeah, better. Okay, so what you have to do in part B, you're gonna launch a projectile, observe the trajectory like I did, record the horizontal distance. So the horizontal distance is 28.2. So my range, which is the X value, is 28.2 meters. That's what you will do in a lab in person, by the way. That's what you will do. So you're actually doing the lab very similar to what you will do in a proper lab setting. Use kinematic equations to calculate the maximum height. Okay. So how do you find the maximum height? If the angle is 37 degrees and the projectile goes a little bit farther, right? Vertically. So the initial speed is 14 meters per second, but that's 14 at this angle. So you are going to find Vx, which is V cosine theta, and Vy, which is V sine theta. So this will be 14 times cosine of 37 degrees, don't forget. And this is 14 times sine of 37. Oop. So with a calculator, just do, 37 cosine multiplied by 14. That's 11.18 meters per second. And here is just 37 sine times 14, 8.43 meters per second. To calculate the maximum height, we need the Vy. Because the extra height or the maximum height is when the vertical velocity is 0. And there is a nice equation, right? V final on y squared is equal to V initial on y squared minus 2gh max, h. V final is 0. V initial on y squared, we have it, is this. So you have this. There, right? Easy. This is oh my God, 8.43 square divided by 2 times 9.81. So 8.43 square divided by 2 divided by 9.81. So 3.62 meters. But the maximum height, H max, is the 10 meters plus 3.62. That's 13.62 meters. That's the maximum height. So how do you check that in the simulation? You're going to use this tool. You see that? Time, range, height. And you're going to look for the maximum height. There, 13.62. Yeah, so perfect match. So my percentage error is 0%. Again, the only difference between a simulation and a real lab setting is that in a real lab setting, you will have a larger margin of error. That's because in a real lab setting, there are more sources of error, right? Systematic, the way you measure the range with a ruler, right? Or a tape, right? The way you measure the speed, the angle, right? It's not perfect with real tools. But still, you're still getting a good sense of what's going on here. And that's not all for part B, by the way. You're going to compare the maximum height, and then you're going to find the theoretical range. So that one is going to be, that's kind of extra, right? So how do you find the theoretical range? Horizontal range. You need to find the total time. You need to find the time it took for the projectile to go up and then to go down. All right? So using kinematics, the total time is a time to go up plus the time to go down. So the time to go up is the time it took to reach the 3.62 meters. You can use the equation B final on y equals to B initial on y minus gravity t. 0 equals to, again, 8.43 minus 9.81 time to go up. The time to go up is 8.43 over 9.81. So it does it quickly. That's 0.86 seconds. How do you find the time to go down? To find the time to go down from maximum height, you use the maximum height. The maximum height is 13.62 meters. That's free fall. 13.62 is equal to 1/2 times gravity times time to go down squared. So time to go down is the square root of 2 times 13.62 divided by 9.81, which is gravity. So the time to go down is 2 times 13.62 divided by 9.81, square root 1.67 seconds. So the total time is 1.67 plus 0.86. There you are. So 1.67 plus 0.86, that's 2.53 seconds. So your range, which is the x value, is what? Is V on x times time. But what's V on x? There, 11.18. So that's 28.29 meters. There you are. Perfect. So the part B is a bit more complex because you have to use the components of the velocity, right? But it's a very interesting lab because that's a good way to review what we have covered in the lecture for this section. All right? Okay, so it says here that you have to do it 3 different times. If you do at least twice, that's good. So for part B, I would say you want to show all this. Part B, yeah. I'm just showing you how I will do it. Doesn't mean that you have to do it like this. I will highlight some of this. All right, don't leave this last for the last minute because then you run out of time to do this work, right? You want to take a snapshot again of this. And remember that I do office hours for this, so if you have questions, you can always stop by the office hours or send me an email about this. Draw the diagram. These are the diagrams, so you don't have to worry about that. Yeah, like reset the simulator and check what happens when you launch at different heights and different angles. So it's just descriptive, right? Like, for example, what happens if I do this more, right? Now you can compare, right? What happened? I increase the angle. What happens if I have 0 degrees like before? Or close to 0? Mhm. So you can describe that, and then you have to write some conclusions explaining the difference between your theoretical and experimental values and what you learn from this experiment. I think it's a very interesting lab. I'm pretty sure that many of you will have a lot of fun with this. And again, it's all about using the simulation for part A and part B. All right. Other than that, again, if you have questions about this, make sure you send me an email or stop by the office hours so we can discuss and I can show you or clarify anything that is not clear. All right. So I will see you guys on the next tutorial video. Make sure you watch this first before you attempt the lab. All right. Um, all right. So see you guys later. I'm gonna stop this now and have a good one. Bye bye.